Welcome again to all of you. So this is lecture 15 of phase equilibria module. So let me just recap what we were doing in the last class, because we left intermittently. So we started looking, so in a couple of lectures back we started looking at phase equilibria in heterogeneous system, and we were taking examples in as far as binary solutions are concerned. So first we had a look at systems with complete miscibility in each other. That is in both liquid and solid state of A and B, which means A and B make a random solid solution in solid state. As a result, the phase diagram that you get for that kind of AB system is isomorphous system, for example Copper-Nickel system. Now the next system that we were looking at was a system in which A and B have partial solid solubility, which means A can accommodate some amount of B and B can accommodate some amount of A before supersaturation happens, and as a result it has profound influence on the free energy composition landscape, which leads to changes in the phase diagram construction. So let me just now go back to what we were doing. So this was the first thing that we did. So we have two elements A and B. Melting point of A is higher than that of B. And what we have here is we have first a temperature T1 which is higher than the melting point of A. As a result, since we can see that if it's a temperature at which is higher than the melting point of both the phases, both the elements, we are going to have liquid phase which is stable than the solid phase. Could be mixture of two solid phases. So in this case it would be a mixture of two solid phases. So what we are going to draw is G alpha and G beta, and both are going to be above the liquid phase. So in this regime the liquid will be the most stable phase as far as T1 is concerned. At T2 temperature, which is intermediate temperature between the melting point of A and melting point of B. So of course it is lower than T1, but it is also lower than Tm of A. I have not drawn the free energy composition plot for T2 is temperature being equal to Tm of A, which is similar to what we drew in the last example. So T2 is between melting points of A and B. So as a result, what you have is you have since temperature is higher than the melting point of B and lower than the melting point of A, the alpha phase, which is the solid solution of B in A, and which has a similar structure as of pure A, starts to stabilize. So the free energy of alpha phase lowers with respect to free energy of liquid, but the free energy of beta phase is still high, which has a structure same as B, and as a result we form two phase region on the A rich side. So on the A rich side, when you are below point A, so we drew first what we drew a common tangent between G alpha and GL, and the intersection of tangent with the point where tangent touches the G alpha and G liquid curves, we denote them as A and B. Below the composition A, it is all alpha, which is solid state, so alpha will be solid. After A but below B composition, you will have two phase region, that is alpha plus liquid, and above B composition you will have only liquid state. So we have alpha, liquid, alpha followed by alpha plus liquid followed by liquid, and then we go to temperature T3, which is lower than the melting point of B. So this is now lower than the melting point of B. So what we have here is both alpha and beta curves are shifted further down with respect to GL curve, and as a result what you have here is you have formation of two phase regions on the two sides of the curve. So we again draw the common tangents between liquid plot and the solid plots. So we denote them the points where tangents touch as C, D, E, F. So below C on the A rich side is the phase field alpha, above C but below D is the two phase region alpha plus liquid, and then we have liquid, because in this region liquid free energy is lower than both alpha and beta. Again we reach a region which is bound by 2 points E and F, which are again the between the common tangent points. So this is beta plus liquid, and on the far right on the B rich side, when the composition is beyond F, which is the B rich region, we have beta phase stabilizing. So you can see how the phase evolution has happened from complete liquid to first the formation of alpha and alpha plus liquid follow and alpha region, now to alpha, alpha plus liquid, liquid, beta plus liquid and beta. So you have complete five phase fields here, and then we move on to a temperature T4, which is lower than both melting points of A and B, but it's slightly higher than the specific temperature called as eutectic temperature. And this eutectic temperature is this is a temperature, I'll explain later what it is, but let's say it's T plus. So at this temperature, the minimas of all the three phases, that is alpha, liquid and beta, are almost at the same level. Since temperature is slightly higher than the T plus, the alpha and beta minimas are slightly shifted up with respect to liquid. So we draw a common tangent again. So it's alpha, alpha plus liquid, liquid region has shrunk quite a bit, and then beta plus liquid and then beta. So again these points are denoted as G, H, I, J. And then we looked at T is equal to TE, which is the eutectic temperature, a specific temperature at which all the three phases are in equilibrium. Now this is where we have all the three minimas on a flat line. So what we have is alpha, alpha plus liquid, liquid denoted just by a straight line, liquid plus beta and beta phase. The moment you go to slightly below the eutectic temperature, the liquid curve shoots up, goes up with respect to alpha and beta, and what we have is a two phase equilibrium, alpha, alpha plus beta and beta. And then when you go to further lower temperatures, what we have is widening of this alpha plus beta regime, and alpha and beta again narrow down a little bit because of decreasing solid solubility in the solid phase. Now we want to construct a phase diagram having got this information. So that is what we will do in the next today's lecture. We started doing in the last class, but unfortunately we didn't have enough time. So this is what we were doing. We will now take it up in today's class. So basically the recap was construction of a phase diagram of AB alloy with limited solid solubility of A and B in each other, which is because of structural differences, size differences, valence differences and so on and so forth, but they do not have vast difference in the melting point. So now let us make this. Right, so this is pure A, pure B, we go from here XB, and this is the temperature axis. Okay, so this could be degree centigrade or Kelvin depending upon how you want to. So let us say first we look at a temperature T1. So let us say this is, let us identify a few temperatures TMA, let us say this is TMB, and let us say this is another temperature. So this is another temperature TE. So let me draw a few lines here. So this is T1 line, this is TMA line, this is TMB line, TE line, and let me draw the TE plus and TE minus a little, sorry, wrong color. So this is TE minus, and that was TE plus, and this is TE minus. So this would be TE plus, and this would be TE minus. All right. They're not very straight, but pardon me for that. So first thing that we observed was we had at T1 everything was liquid. Okay. At a temperature T2, which is between TMA and, so of course at TMA both solid and liquid phases will be in equilibrium. At temperature T1 we had alpha region somewhere here, followed by liquid region. So this is, now let's label it, this is alpha, alpha plus liquid, and liquid, and let us mark these points at as red. Okay. So the first one is here, last another one would be at somewhere here. Okay. Now at T2 temperature, now this is at T1, sorry, this is at T2, this is T2. T3 was a temperature. Let me see where the T3 was. So let me mark these temperatures as well, T4, T5, T4, T5 and T6. So T3 was lower than the melting point of B. Let's go back here. T3 was lower than melting point of B, so this would be T3. Okay. So let's say this is T3. Let me draw again a horizontal line at T3. Okay. Now at T3 what we will have is, so this is point A, B. Now we will have C, D, E, F. So let me choose red color. So my next point is, we are at T3. So we are somewhere here in terms of the other point C. So we have alpha. So this is alpha, followed by, we'll have alpha plus liquid, followed by we'll have liquid, followed by we'll have, so this is beta, and this is liquid plus and beta. And now we are near another point. So now we are at T4. So this is T4. So when we go to T4, this point is somewhere here. So for the sake of simplicity, let's move these points a little bit so that they fall on a nice curve. Okay. So it would be somewhere here. Okay. So if I now make the other points, it will be somewhere here, this would be somewhere here, this would be somewhere here, and this would be somewhere here. So this is again, so this is alpha plus liquid, liquid, liquid plus beta, beta. This is again alpha, alpha plus liquid, this is liquid plus beta, beta. And now we go to T5. So at T5 there is only one point for liquid, this is liquid, and this is alpha. Okay, so what we have here is alpha, alpha plus liquid, liquid, and then when we go to beta, when we go to T6, which is this temperature, it is alpha and beta have shifted a little bit here. So what you have is alpha, beta, and you have alpha plus beta, and here you had alpha, alpha plus liquid, liquid here, liquid plus beta and beta. Now let us try to connect the dots. So when we try to connect the dots, so the first dot is something like this, this and this. Okay, it's not very straight as it should be. So okay, and first let us, so you will have to pardon me a little bit for this kind of boundaries turning curvy. They are not so curvy in reality, and have this kind of, so let us say this point is this, so this is the beta point, and then we connect a lower temperature. This is for lower temperature part. Just 1 second, do this is the lower temperature part. Okay, and then we had a T7 where alpha and beta shifted even, so this would be, let us say T7. So at T7 it was here, let us say it is here, and when we connect the dots it would be somewhere here, something like that. So what you will have is here, so this is the TE line. Up to this point liquid and beta coexist and liquid and solid coexist. After this line only solid phases coexist, and within this region, so if you can take this further down, it will come like this if you had more free energy curves. So this is at T7, alpha, alpha plus beta and beta. So if you look at the phase diagram now, what we have established here is you have a liquid phase here. Liquid phase, as the temperature decreases, liquid phase first forms into alpha plus liquid, then as for this composition, if you had this composition, liquid phase will convert into beta first, and this liquid plus beta will slowly convert into alpha plus beta. So you form this kind of phase diagram where you have two regions of complete solid on the right and left. These are called as terminal solid solutions of alpha and beta, solid solution of B in A and A in B. On the high temperature side you have liquid only. In the intermediate temperatures and intermediate compositions, what you have is a two phase region, liquid plus alpha and liquid plus solid. Unlike isomorphous system, there are two liquid plus solid regions, one is liquid plus solid 1, second is the liquid plus solid 2, alpha or beta. And then at lower temperatures and in the intermediate compositions, you do not have alpha and beta alone, you have a mixture of alpha and beta. And there is a specific temperature at which is called as TE, which we call as eutectic temperature. At this temperature, liquid of this composition, which is called as CE, the eutectic composition, directly transforms into two solid phases alpha and beta, and this temperature is lower than the both melting point and of A and B. So this kind of phase diagram that we obtain when A and B have limited solid solubility into each other, but their melting points are not vastly different, this is called as a eutectic phase diagram. And basically what happens is that, so this phase diagram is characterized by phase reaction in which liquid of composition CE, so CE is basically CE percentage of XB, okay. So it is in the mole percent of XB, transforms into solid phase alpha of composition C alpha and transforms into beta phase, which is composition of C beta. So this is, I would say, C alpha, and this I would say is C beta, and this is CE. So this is at this temperature. So I will tell you now how the microstructure evolves later on. So this is at cooling. You can also heat it, so it is a reversible process, and then alpha plus beta which exists at this composition will convert into liquid of composition C. So this is what is the characteristics of this phase diagram. It is called as eutectic phase diagram, and this reaction is called as eutectic reaction. And it is at this temperature you can see the three phases coexist. At this line you can see that at this point liquid and alpha plus beta all three coexist, which was marked by free energy minimum being at the same height at the same level for all the three phases. So at this point your three phases coexist together, whereas in the other regions you can see that in this region liquid phase exists, in this region alpha phase exists, in this region beta phase. So there are three single phase regions and then there are three two phase regions. This is the region between alpha plus liquid, this is the region between liquid and beta, which is liquid plus beta, and the region between two solid phases alpha plus beta. Again, the terminology wise, this boundary is called as liquidus, which is the boundary between liquid and the first solid. Both of these are liquidus. These are solidus. And these two boundaries are called as solvus. Mixture of alpha and beta is called as eutectic mixture. And eutectic mixture, the overall composition of this mixture will be same as Ce, but alpha will be of composition C alpha and beta will be of composition C beta. We will discuss this phase diagram a little later in terms of how the phases evolve. So so if you look at a good phase diagram, how it looks like. So the previous one was the phase diagram that we constructed, which was not very neat as far as drawing was concerned. So what you will obtain is something like this. So this would be the liquid region, this would be liquid plus alpha, this would be alpha, this would be alpha plus beta, liquid plus beta, and this would be beta. So this looks like a more neat diagrams, and this is Tm of B, this is Tm of A. So this would be a eutectic phase diagram, and these alpha and beta can have different structures, but alpha and beta can also have similar structures, alpha 1 and alpha 2 for instance. So this phase diagram, for example, you have systems like lead tin alloy, which is a very important soldering material. It follows this kind of phase diagram. So other than these two kinds of phase diagram that we discussed, one is the isomorphous phase diagram. We evolved them on the basis of free energy composition changes. You can have other diagrams as well. For instance, you can have situations where you can have high free energy of mixing, for instance. You can have systems which have systems with a miscibility gap. So miscibility gap, now what I would do is that I would take a reverse approach here. So systems with a miscibility gap means for these materials delta H mix in solid state is larger than delta H mix in liquid state, which is equal to 0. Okay. So basically A and B are soluble in liquid phase. But may not be in the solid state. So I will not spend too much time on it. I will just go through a few phase boundaries. So for example, we can have a scenario in which let us say at a temperature T1, which is greater than the melting point of let us say TMB is higher than so TMA is TMA, which is higher than TMB. This is the scenario. The first scenario is like this, T1. So you have XA, XB, and let us say the scenario is something like this. You have GS and you have GL, this is G. Then you come to a temperature, different temperature. At this temperature, the free energy curve shifts a bit. So you have this is the free energy curve of solid phase, this is the free energy curve of liquid phase. So this temperature T2 is lower than Tm of A but higher than Tm of B. So this is, we will redraw it. So you had there is a free energy of solid phase, there is a free energy of liquid phase. So GS, GL, this is the common tangent that we draw. This is solid, this is liquid plus solid, and this is liquid. So this is A, this is B. Now you come to another temperature. A, B, and this temperature is T3, which is lower than Tm of B. So what you have a situation like this, you have free energy, oops, not very neat. So this is GL. I will draw the solid phases a little differently. The solid phase is a bit like this. So this is GS, and when you draw the common tangent now, you can draw the common tangent here and you can draw a common tangent here. So these are 4 points. So you will have solid, you will have solid plus liquid, you will have liquid, solid plus liquid, and solid. Okay. So this is, let's say, C, D, E, F. You lower the temperature further down, and let's say you reach a temperature T4, which is lower than T3. At this temperature, your GS, GL, P. Okay, so up to this point it sounds all right. Now it seems a bit strange in one sense that you had single phase region liquid followed by one two phase region, and then you had two phase regions. So somewhere in between the solid, so the liquid phase is liquidus and solidus are a little different. Now let us go to temperature T5. So at T5 your liquidus is something like this, and solid free energy curve changes a bit. Solid free energy curve takes this form. So now the solid has basically phase separated into different composition. So this is S1, S1 plus S2 and S2. So when you construct the phase diagram for such a system, the phase diagram, I will not get into details of now phase diagrams, unlike in T and XB. What you will have is something like this. You will have so you have liquid plus solid, liquid plus solid, and then at lower temperatures, and here also you had solid, but then this solid has broken at decomposed into two different solids at So, you can see that a free energy curve for solid develops a curvature here, a negative curvature at this point, at which temperature it phase separates into two solid phases. So, I will stop here at this point. What we have looked at is basically the eutectic phase diagram and a phase diagram of a system in which solid is immiscible in the solid phase, A and B are immiscible in the solid phase itself. We will come back to a few more variations of phase diagrams in next lecture. Thank you.